Hello everyone, and welcome back to my YouTube channel or the VIG Structure Hub. This is a place where you learn, build, and innovate. In today's lesson, I want to continue with dams and retaining walls, and today I will be specifically tackling stability of dams. So if you are a Module 2 student, this session is for you. Also, those students who are pursuing SIDAC, this lesson is for you. And also any trainer who is willing to learn with me, also you can join me. So let's go back to our topic of today, which is stability of dams. So, and if you have not subscribed to this channel, please don't forget to subscribe and hit that notification bell so that you may get more updates from the VIG Structural Hub. So stay tuned as I start up to the end. Stability of a dam. So what is stability of a dam? So this one, it refers to its ability to remain safe, functional, and upright under various conditions, such as water pressure, seismic forces, and environmental changes. So refers to its ability to remain safe, functional, and upright under various conditions, such as water pressure, seismic, so that is what we call stability of a dam. So if I may repeat, it refers to its ability to remain safe, functional, and upright under various conditions, such as water pressure, seismic forces, and environmental changes. A dam should be stable under all conditions. Under conditions, but the dam may fail by number one, by sliding of the soil on which it rests, Number 2, by overturning. Number 3, due to tension stresses. And then number 4, due to excessive compression stresses. So a dam should be stable under all conditions, but the dam may fail by number 1, sliding of the soil on which it rests. Number 2, by overturning. Number 3, due to tension stresses developed. Then number 4, due to excessive compression stresses. So I will start by number 1, which is by sliding of the soil on which it rests. So we start by number 1, which is sliding. So under sliding, we are going to look at conditions to prevent the sliding of a dam. The condition to prevent the sliding of a dam. So I will draw a dam here, a masonry dam, and a water it is retaining from. So let me draw it here. So this is a dam, a masonry dam, and this is a reservoir or a body of water. So this dam is holding this water back. So this water, it has a height of h. So this is the height of water. And this dam has a height capital H. So this water is exerting pressure on the side, on one side of this trapezoidal dam. So we draw this pressure. So this is force, which is a pressure as a result of the water. And this force is acting at a height of h/3 from the base. So this is h/3. Again, this masonry dam, it has a weight W at the center of this trapezoidal dam. So this is the weight of the dam. So you call it W, and this is the center of gravity. This is force F. Again, this force F and weight of the dam, which is W, it produces a resultant force, which is R. Like that. So this is R. So let's name this dam. So this is point A, this is point N, this is point M, and this is point B. So the distance from N to M is distance X. So this is distance X. And the distance from A to M is distance D. So this is distance D. And the distance from A to B is distance B. So let's analyze this dam and see how the sliding will occur. So the forces acting on the dam are F, which is this force. So this force, it acts. This force F, so forces acting on the dam. So this one is equal to, number one, is force F. It is acting, this force F, acting at a height of h/3 from the base. We have another force, which is the weight of the dam. So number two, weight of the dam, which is W, like that. and is passing through point and is acting vertically and is acting vertically through the COG, the center of gravity of the dam. So we have the resultant force R. So this is the resultant force R, which is as a result of force F and W, and is passing through point M, this point. So this dam will be in equilibrium if force R equal to R is applied at point M. So this force R is equal to this R applied to point M in opposite direction of R. So as you can see, this is in the opposite direction of this R. So R is the reaction of the dam. So this R is the reaction of this dam, which can be resolved into two components, which is W. So W, vertical component, and friction force at the base of the dam, horizontal component. So the friction will be at the base. So that is the friction, like that. So let me rub here to create more space for calculation or for more analysis. So let mu be the coefficient of friction between the base of the dam and the soil. So this is the base of the dam, and here is the soil. So the maximum force of friction is given by F max is equal to mu times W. So that is the maximum force of friction is given by F max is equal to mu times W. If the force of friction, i.e., if the force of friction, i.e., F max, is more than the force due to water pressure which is F. So this F, if the F max is more than the force due to water pressure, due to water pressure produced at this point, then the dam will be safe against sliding. The dam will be safe against sliding. Like that. So in short, the F max, which is mu times W, should be greater than this force produced by water pressure. And in such a case, the dam is safe against sliding. So in short, F max, which is M, mu, not M, times W, should be greater than F for a dam to be safe against sliding. So you will be checking this during your calculation to see whether this F max is greater than F or not. So at the end, you'll be able to know if the dam is safe against sliding or it's not safe against sliding. So that is all about sliding. We proceed to number 2, which is overturning. Overturning. So I will retain this diagram for explanation, for explaining overturning. So number 2 is overturning. So for overturning, if the resultant R of the weight W of the dam, so if the resultant R as a result of the weight of the dam W and the horizontal force F due to water pressure strike the base within its width, the point M lies within the base AB, there will be no overturning of the dam. So I will repeat, if the resultant R, this resultant R of the weight of the dam and the horizontal force F, W and F. So this R is as a result of the weight of the dam, which is W, and F. Strike the base within its width. So if it strike the base, which is at this point M, the point M lies within the base AB. So as you can see, this point M, it lies within the base AB. Then there will be no overturning of the dam. So in short, it means if the resultant R, so if R, it cuts, if R cuts at M and M lies within A and B, then it means no overturning. No overturning of the dam. like that. So let's prove this statement. I want to prove this statement. So let's prove allow me to erase here. So I'm going to prove this statement by taking moment at point M, at this point M. So taking moment about point M, taking moment about point M, moment due to horizontal force F about M, moment due to horizontal force, which is F about M, will be given by, so this is F. So we know that moment is force times perpendicular distance. So this is force F. And for you to get the perpendicular distance from F, from this force F to where our M is, so from here to here, is h over 3. So it will be F times small h over 3. So that is moment due to horizontal force F. Again, we have moment due to weight W of the dam about point M. So moment of weight W of the dam about point M. Again, you know that moment is force times perpendicular distance. So this is our weight, and our perpendicular distance is from here to here, which is x. So it means this moment is equal to W times x, like that. So this moment, as a result of force F, it tends to overturn this dam about point B. But the moment of weight of the dam W tend to restore the dam, against overturning. So this moment, as a result of W, which is the weight of the dam, it tends to restore this dam against overturning. So if the moment as a result of the weight will be more than the moment as a result of this F, then it means there will be no overturning of the dam. Let me write here, if the moment due to the weight due to the weight W is more than the moment due to F, then there will be no overturning of the dam. Like that. For equilibrium of the dam, the moment should be equal. So for equilibrium, of the dam, the moment should be equal. The moment i.e. F times H over 3 should be equal to W times X, like that. But since overturning can take place about point B, this point B, then it means restoring moment about point B is equal to W times NB. Since overturning can take place at point B, then the restoring moment, is equal to W times NB, like that. But overturning moment due to force F about point B is equal to, but overturning moment due to force F about point B is equal to, F times H over 3, which is equal to W times X. So this is the overturning moment due to force F about point B. So there will be no overturning about point B if restoring moment about point B is more than the overturning moment about point B. So there will be no overturning moment. There will be no moments about point B if the restoring moment about B is more than the overturning moment about B, i.e. W times NB should be greater than W times X. So this is W times NB should be greater than W times distance X, or NB should be greater than X, whereby or which imply NB should be greater than NM. So NM, here is NM, which is distance X. So this means that there will be no overturning of the dam if point M lies between N and B or between A and B. So this is the last statement. There will be no overturning if there will be no overturning of the dam if point M, this is point M, lies between N and B, or A and B. And that is all about overturning. So I will explain the last statement using the diagram. So there will be no overturning if the dam, there will be no overturning of the dam if point M, so this is point M, lies between N and B. So it should be in between N, point N and B, and B, or no, or A and B, or A and B. So this is point A and B. So this point M should be between N and B, or A and B, to prevent overturning. We proceed to tension. So we proceed to number 3, which is tension. Again, I will keep the diagram for tension. So number 3 is tension. So in tension, so we will talk about condition to avoid tension in masonry of dam at its base. So condition to avoid tension in the masonry of the dam at its base. Like that. So we know that a masonry of a dam is weak in tension, and hence the tension in the masonry should be avoided. The maximum and minimum stresses across the base of the dam are given by, so the maximum stresses across the base of the dam is given by over B plus 6 times W times eccentricity over B square. So if we can take W over B, or we can factorize by taking W over B outside, then we open the bracket, we'll have 1 plus 6 E over B. So that is the formula for getting maximum stresses across the base of the dam. And this maximum, it occurs at B. And then we proceed to the minimum stresses across the base of the dam. So the minimum stresses across the base of the dam is given by W over B minus W times 6 times E over B square. Then we factorize, we will end up having W over B into bracket 1 minus 6 eccentricity over B. So this is the formula for minimum stresses across the base of the dam. So, and we know that stress given by, so stress given by 1 minus 6 E over B is negative. Which means there will be tension in this area under the formula 1 minus 6E over B. So in the limiting case, there will be no tensile, stress at the base. at the base of the dam, if 1, this formula 1 minus 6 E over B is greater than or equal to 0, or B minus 6 E should be greater than or equal to 0. So you multiply both sides, each term by B, so B will cancel with B. So 1 times B will be B, and then 6 times E will remain, and then B times 0, it will be 0. So or B minus 6 E should be greater than or equal to 0. Again, if this 6 minus E crosses to the other side, it changes from negative to positive. So we will end up having B is greater than 6E, like that. Or you can also divide both sides by 6 by 6. So it means E is less than or equal to B over 6. So this is our first case. So you have E is less than or equal to B over 6, like that. And then we know that E is equal to eccentricity. And eccentricity is given by, so E is given by D minus B over 2. So D minus a half of B. So if you can substitute this in this formula, we'll end up having D minus B over 2 is less or equal to B over 6. Then this minus B over 2, if it crosses to the other side, it will change from negative to positive. So we'll end up having, which imply D is less or equal to B over 6 plus B over 2. The LCM is 6. So LCM is 6. So 6 into 6 is 1 times B is B, plus 2 into 6 is 3 times B, 3B. So which imply D is less or equal to B plus 3B is 4B, 4B over 6. So 2 here 2, 2 here 3. So we'll end up having D less or equal to 2 over 3B. So there will be no tension in masonry of the dam at its base if E is less or equal to B over 6 or D is less or equal to 2 over 3B. So these are a very important two formulas to check whether there will be tension or not tension in the masonry wall. Again, we proceed to the last item, which is compression. And this is a statement. So the condition to avoid the excessive compressive stresses at the base of the dam, the condition to avoid the excessive compressive stresses in the masonry of the dam is that the maximum stress in the masonry should be less than the permissible stress in the masonry wall. So number 4, compression. So condition to avoid the excessive compressive stress at the base of the dam. So the condition is the maximum stress in the masonry should be less than the permissible stress in the masonry. And that marked the end of stability of dams. When we meet in the next session, I will start tackling examples concerning stability of a dam. And more examples will be coming from past papers, that is Kenya National Examination Council and the CDAC. So we meet again in my next session.